have at worst poles. So that's what removable singularity is. So the whole point of this consistency condition is telling me that I have lots of different equations that are isomorphic. So I'm thinking of that as lots of symmetries. The new differential equations, at least as far as 0 and infinity are concerned, if we ignore 0 and infinity, these equations have completely new different singular points. So these ones couldn't be too bad. So they're removable. Okay. So in particular, that means that if I have a solution, it's a nice point, I can continue it. Let me not say. So this was 1, 2. So these are equivalent. Let's look at 0. So at 0, I said I have this solution p of x, x to the L, e to the q of x. And it's equivalent to, so that means I have some v of x. The solution I get when I multiply by q So, here at 0, I have a solution more or less of the same form. I said that the Q was diagonal with polynomial entries, and they're unique up to permutation. So there's some polynomial here, which equals another entry when I plug in Q. Well, I keep doing that. Eventually, I'll repeat myself. I'll have some polynomial, in rational powers, some diagonal entry, which equals the same thing when I plug Q in. Now again, I use the fact that Q is not a root of unity. This can't happen unless P is constant. But if you look carefully, I arranged that the polynomials here have no constant entries. So they're all 0. So these guys are gone, and we're left with a regular singular point. So this is the flavor of all the proofs. They get a lot harder. But the proofs all go by looking at the singular points and showing that they're particularly simple. When I have two Q difference equations, the key is to show it's regular singular in the sense that Julian mentioned. And, well, it requires more and more work. Okay, so that's that. So what? I now want to claim that, just look again at the differential equation, and I want to claim that it can be simplified. Okay. I've forgotten why. Let me say why. So in philosophical terms, if you have removable singular points, you can remove them. And you can remove all of them. This is you can remove them all at once. You can do it algorithmically. This is a nice result of Varka 2 and Susie Mata that appeared in the last ESOC conference. But in any case, so you could do an equivalent system where the only singular points are 0 and infinity. And they're regular. Now, if you have a differential equation with no singular points except 0 and infinity, it's completely determined by its monodromy. And I'll say what that means, and it's equivalent to this. So let's see. Since I have time, let me give the proof. So I'm giving these proofs because I feel that you'll learn something more than just these results. You'll learn why it's interesting to look at singular points. You'll learn why it's interesting to look at equivalent systems. And now you'll know why it's interesting to look at monodromy. So I have this equation. Just skip the 1. And here's the sphere. Here's 0. Here's infinity. I take some y of x. We've seen this picture before. And I continue it analytically around some path, gamma, and I'll get some new solution, which is the old solution times some gamma. Okay. And now I'm going to I'm going to assume that this field C is a subfield of the complex numbers. This can be arranged. And I'm going to write m sub gamma as e to the 2 pi b for some matrix B1. And I'm going to look at this, y sub x equals I want z sub gamma to equal e to the b1 log x. So dz dx is b1. Maybe I got the next there. Yeah. And now it's just a question of looking at my y. And I always do this backwards. Hopefully this works out. And this d of x. When I analytically continue this around a path, I'm going to get a m gamma here and an m gamma inverse there. So this, you just have to do the calculation. This is single valued analytic in the punctured sphere. Both of these satisfy singular differential equations that are regular singular. The other characterization of regular singular is that solutions of those equations behave nicely. Their growth rate is bounded above and below by powers of x. So I have something single-valued analytic that's bounded, its growth, let's say at 0, is bounded by a power of x. It can be continued to 0 to be meromorphic at 0, meromorphic at infinity. We have a single-valued meromorphic function on the sphere, so it's rational. So this gives you my change of basis, and the equivalence between this equation and this equation. So that's the story. And well, if you do the same thing to the difference equation, if you apply the same transformation, the calculation will give you that it's equivalent to a constant equation. I'm not going to do that. So that's the proof. These simple, this consistency condition says that the original equation is equivalent to lots of other equations. Those equations, their singular points are related to the original singular points. on the finite plane, they're removable. At infinity, they get there's so many symmetries that they have to be regular. And then you get this. Okay. But I'm not done. So are there questions? Can people bear with me still? I want to talk about Galois theory. Yeah?
So in this case, you use Turretin's theorem. This is the main point. So in the other cases, you also...
So let's talk about the two Mahler case. So we start with your paper. So Julien showed that locally, for a Q difference, a Mahler equation, you can put it in triangular form, right, with constant entries along the diagonal, the matrix. And then, this really, again, it's Shefka. He shows that you can remove the off-diagonal entries. And it's a very complicated proof, given that you have another equation. So it's the other equation. There are too many symmetries, and they have to disappear. So it's a technical proof. By the way, in the shift case, dy dx, you have y of x plus 1 is something times y. There's, again, all the singular points on the finite plane are removable. You still have a point at infinity. And in order to show that it's regular, at some point you need to use some analysis. Very little, a little bit of resummation. But I don't want to say, oh, it's just a technicality, but it isn't. But the philosophy is the same. In these situations, most of the singular points disappear. The ones that don't disappear are nice. That's the philosophy. Okay. Galois theory. So I have three more slides. I'm not assuming that everybody knows Galois theory, so let me quickly tell you the key parts. So this is the Galois theory of difference equations, my version. You start with some field. They're generalizations, but this is the basic thing. You have a field, the elements that are left, and an automorphism. Again, you can do it with an endomorphism, but an automorphism. The things that are left fixed are called constants. You have an equation. You have a place where the equation has a full system of solutions. Some ring where you have a matrix, an n by n matrix of solutions. And in order to make things unique and to be able to make things well-defined, you can, if you assume that the constants are algebraically closed, if you look at something that's simple, in some sense a minimal extension, then it will be unique. So this is like the splitting field. Then the Galois group is the group of automorphisms of the ring that commute with the sigma. Don't want to go into the finer structure because it's not necessary. So the Galois group it can be identified with the linear algebraic group. You think about it for a second. If you apply an automorphism to the solutions, you'll get solutions back, so they must come from your original solutions by some change of basis. So you can identify the automorphisms with invertible matrices, and it turns out that they form a linear algebraic group. And just as in the usual Galois theory, the size of the group measures the number of relations among your solutions. The bigger the size, the smaller the number of relations. The more symmetries you have, the less complicated things are. So this ring isn't a may have zero divisors. So when I say transcendence degree, I mean, if it didn't have zero divisors, it would be the transcendence degree. Good. So here's an example. This is the equation for the gamma function. One can show that the Galois group is the full group of 1-by-1 matrices. This has dimension 1. So the transcendence degree when you adjoin gamma of x is 1. That just means it's transcendental. Okay. That's it. Differential Galois theory of difference equations. So here I have a difference equation, and I want to measure the differential relations among the solutions.
I'm sorry, about a question about previous slide. Do you have Galois correspondence?
You do, but not at the level of the ring. So you need to take a total quotient ring. So you invert everything that could possibly be inverted. And then you have a correspondence between closed subgroups and certain kinds of subrings. Okay. And we do the same thing. So I start with a field. Now I have an automorphism like the shift and a derivation, like ddx. And again, I want to look at the things that are left invariant by the automorphism. And before I assumed it was algebraically closed, here I'm going to assume that it's differentially closed. So it's nice to have logicians in the room. I don't have to explain it to them. But to the others, it just means that any system of differential equations that's consistent, it has a solution somewhere, will have a solution in this field. Start with an equation. I again adjoin a solution. I join a solution, and now I get the when I apply sigma to the solution, I just multiply it by a, so I don't have to worry about shifts, but I don't get the derivatives for free. So I throw in all the derivatives. So it's a very big object, very fitting. Such a thing exists. And the Galois group is the group of automorphisms that commute with the automorphism and the derivation. And we have a Galois theory. This Galois group can be identified with matrices with entries in this C, this very large differentially closed field, and it's a differential group. Okay, so it's the set of matrices whose entries satisfy some fixed set of differential equations. And the differential dimension, again, measures the differential transcendence degree. That is the number of elements, maximal number of elements that satisfy no differential relation. And the key fact is that the Zariski closure of this group is the standard Galois group. So if I think of this equation just as an equation with respect to sigma, morphism, it has a Galois group. This sigma delta group lives inside, and it's Zariski closure. It's the whole thing. So here, one can calculate that for the gamma function, this Galois group is again the full invertible matrices with entries in C. It has differential transcendence 1, so this is hypertranscendental. It satisfies no differential equation. So this looks like it has nothing to do with what I said before, but it does. How does one show that a solution of a linear difference equation actually satisfies no differential equation. While you try and calculate the Galois group, you will first show that the usual difference Galois group is large. Let's say it's SLN. And then you show that this sigma delta group is not a proper subgroup. It's not a proper subgroup, it has to be large. SLN, it has dimension n, but it also has differential dimension n. So the Galois group will be very large, and that's that. So here's some useful facts. Theorem of Phyllis says that, for instance, if you've shown that the usual sigma Galois group is SLN, the sigma delta Galois group, it's going to be Zariski dense. There's only one possibility other than the whole group, and that'll be SLN of the constants. So the Galois group could just be, a priori, it's either SLN of C, that is the delta constants, and I'm saying the only other possibility is the subfield of this German C that's killed by delta. So there are just two possibilities. And now we come to this notion of integrability, and it's a strong form of consistency. So in these situations, sigma and delta commute, so the consistency condition is actually the commutation. So it's just what we call integrability. Fine, here's the theorem. If you look at sigma being either any of these, either multiplication by q, the shift, or you have to be a little careful. In this case, I'm not going to go into the details. The Galois group, the sigma delta Galois group of integrable equations is always a subgroup of this particular, it will be commutative. So the final conclusion is the following. If your sigma Galois group is semi-simple, then the two different Galois groups coincide in the sense that, as algebraic groups, they coincide. And so if a difference equation has this as its Galois group, then the solutions will be hypertranscendental. You can say more. And this kind of result is in this, there are these two very nice papers of Julien and Dreyfus and Ardoin, where they use the original results of Ramis and Bézavin to prove this from those results directly. As far as I can tell, I don't think you get this result. No. But you I mean, they're really nice papers, and they show that all kinds of interesting functions satisfy differential equations. And Carlos and I, we've worked on this case, and again, for the experts, the case of projected integrability, which is a weaker form of integrability. And using these, you can show that lots of functions that satisfy difference equations satisfy no differential equations. So that's it. So, thank you.
So do we have any questions?
Yes.
I'm sorry, the G sub m in the theorem, G sub a, G sub a, that is, again,
This is the
sorry. Oh.
the one-by-one invertible matrices, multiplicative.
Okay.
The multiplicative group of the field, and this is the additive group of the field.
Okay, thanks, sorry.
One group of geometric components is this form. It looks strange because there's
So
is there an easy way to see why there are just two single
So for the shift, there's just one. The group of connected components is cyclic, and that's related to the fact that you cannot extend the shift to a finite algebraic extension of C of x. For the Q case, you can extend to C of x. You can take roots, square root of x, and you can extend Q of x to that. I don't know if that gives enough of a hint. I can explain it in more detail. You will always get the possibility of at least one cyclic extension because of the structure of.
Yeah. Why not more than two?
So, and it's technical, but for the for the shift, you get just one, at most one, and for Q of x, it's a similar reason. And for the Mahler operator, turns out that the Mahler operator is in many respects the same as the Q shift. That is, the Mahler operator acts on log x the way the Q shift acts on x. And once you think about that a little bit, many results follow.
Any other questions? So let's thank Michael again.